Okay, so moving on with the 6502 emulator, I thought I'd have a crack at subtract with carry. And this is the definition of subtract with carry here. It's you take the A register, you subtract a value from memory, and then you subtract 1 minus the carry flag. So that seems a little bit odd because that isn't how add with carry worked. Add with carry worked by taking the accumulator, adding to memory, and then adding the carry flag. So it's a little bit odd that subtract with carry would do something weird like subtract 1 minus the carry bit. But what it's doing is it is using the carry flag as a, instead of a carry, it's using it as a borrow. So when you're doing subtraction, if you can't do the subtraction correctly on the digits that you're trying to subtract, you'd borrow from the next column and then use that to get your subtraction in that column, and the borrow can flow through. And that's exactly how carry really works. Carry is doing the same thing except it's adding on to the next column instead of borrowing from it. So that's all great. So we could go through and implement subtract with carry the way it's done there, but one of the things I was looking at is like, why is it subtracting 1 minus the carry? And that's the bit that I didn't understand, because if you subtract 1 minus the carry, then when you flip the carry bit and then you start doing the borrow, but you don't flip the borrow bits. It's like, it seems mental until you realize how this has been implemented in the hardware, because it doesn't actually say on here, it just says it works like this, which it does. That is the definition of how it works. It subtracts the contents of memory location to the accumulator together with the not of the carry bit. And if an overflow occurs, the carry bit is clear and enables multiple byte subtraction. So yeah, totally right. So the reason why it's done like this, I believe, is because it basically allows them to use the addition circuitry that they would have built in their 6502. They can use the addition circuitry to do the subtraction. If we have a look at that, this is subtract with carry. Sorry, I still don't have a tablet, so you're gonna have to put up with my janky mouse thing. So one of the things you could define is if you take A minus B equals C. That is exactly the same as doing A plus minus B equals C. So if you could flip the sign, you could actually do an addition instead of subtraction. And the same would be true of if you did A minus negative B equals C is the same as doing A plus B equals C. So these two are equivalent, and these two are equivalent. So if you can flip the sign of your operand here, then you can do this as an addition instead of a subtraction, and then you can just reuse all the circuitry that you've built to do your subtraction. Now we could do the same thing with our code. We could reuse our addition code. The only weird thing is this is subtract with carry. So there's actually another thing to subtract on here as well. That's just the A and the operand, but what about the carry flag that we want to subtract from that? That would involve subtracting an extra 1 or possibly a 0 from this value. So it doesn't seem like any advantage in trying to do it this way until you think about how signed numbers are implemented in the processor. In fact, in most processors actually, basically as 2's complement. So what you do is if you want to negate any particular value, so let's just say let's say it's an 8-bit value because we've got an 8-bit processor here. 1, 2, 3, 4, 5, 6, 7, 8. So that represents the value 1. So if we want to negate that value, so this is called 2's complement method, is to negate that you flip the bits and you add 1. So that's our definition of what a negative version of that is. So if we want -1, we flip all the bits. So we want to, so we flip those bits, but we also add 1 to it. So that takes that 0 and makes it a 1. So if this is in decimal now, if this is decimal 1, then this is -1. And that's the way we represent it. And you can see it's been flipped because it's got this sign bit on here showing you that it's basically negative. That's our definition of the sign bit. And if you consider that the sign bit there, you can see that one, because it's not set, is positive. And this even works with the value 0 Because if you take the value 0 and you negate it, you get 1. And then if you add 1 to that, well, you get all your zeros back, because it wraps around to 0. So actually what ends up happening is you negate it and add 1 and you get your 0 back. Whoa. There it is. So 0, the negative version of 0 is 0, and all the other values flip correctly. So even 0 flips correctly using this. If it didn't, it'd be rubbish really. If you flipped to 0 and you got a negative 20 or something, it'd be pretty awful. So how does that help us with the subtract with carry? Well, what that means is, so if we take any value, let's say we want to take 1 minus 1, and we'll subtract 1 from it, like so. What we can do, this is going to be our answer down here. So what we can do instead of doing the subtraction is we'll turn this into an addition, and we'll flip the bits on this and then add 1. So we'll flip all this round. We just did this before. Flip this round. Gives us a 0 there, but then we add 1 to give us that. So this is going to give me 1 minus 1 should give me the answer of 0. So 1 plus 1 is 1, 0. 1 plus 1 is 1, 0 with the carry, 0 with the carry. And you see where this is going. And there's a carry of 1, and we carried a 1. So we flipped our 1 minus 1, and we actually did it as 1 plus negative 1. And we actually got the answer, correct answer, 0. And then we got a 1 in the carry. So what's the advantage of having the flipped carry bit? Well, this is where if you flip the number and add 1, this is where the carry bit's coming in. So this clearly must be how the 6502 is doing its addition. So we've done a previous subtraction and it didn't result in a carry. What we do then is we put the opposite of that into the carry bit. We actually shove a 1 into the carry bit. Now that makes loads of sense, because now if we've got a 1 in the carry bit down here, and then we want to do our, let's say 1 minus 1, we'll flip the bits. So we'll do I'll write down the 1 here. 3, 4, 5, 6, 7, 1. So we don't want to do our 1 there, and we want to subtract just 1 from it. So again, 1 is the same number as that. So I'll write it down here, but then we'll flip the bits like we said we were going to. Flip the bits like that, and then we have to add 1 to it. But guess what? We've already stuck a 1 in the carry bit. So now we don't need to do the add 1 because it's going to do it for us. So that's like, this is the way it's working out basically, that we've turned our 1 minus 1 into an addition sum. And all we really had to do was just flip the bits on the operand, and we didn't even have to actually do anything with the, we didn't have to do the add 1 or not, because it's doing it for us basically. So if there was no carry from the previous subtraction, we put a 1 in there and it's going to flip it for us. Now if there was a carry, then it's going to put a 0 in there, and that kind of makes sense, because if you want to do the negate and add 1, well this carry is a borrow, so it means subtract 1. So you're doing add 1, subtract 1, and that just means you can just flip the bits again and just leave it the way it is. So in all cases this just totally works out, that basically all they're having to do to get subtraction to work is flip the bits on the operand, add just as normal, on the basis that subtraction has left us with the not of the carry bit, not the actual carry bit. So that's a bit confusing. They've put a bit of work onto the programmer there, because the programmer then has to set carry bits instead of clearing them and stuff like that. But hey, that's just the way it is. This was our 1 minus 1, and we had no carry from a previous subtraction. So all we did was we negated those bits, and then we're going to do 1, and then we're going to do it as an addition, remember the subtraction? So we're going to do 1 plus 1 is 1, 0. There we go, and you see that you get the correct answer of 1 minus 1 with a carry of 1. So 1 minus 1 is 0. And of course we got a carry of 1 out of there, and I believe that we just stick that 1 straight back into the carry flag, and that shows that there was no carry in this case. I think that's how it works, because this 1 minus 1 didn't produce I didn't produce a borrow, but we got one out here at the end. And I assume that we just stick that in as it is, so we don't have to do anything else with that. And that would come out as a 0. Yeah, and that would come out as a 1 at the other end, meaning we don't have to do anything special. It just negates and it all works. So I actually think that's actually really clever, if that is the way it's working. I mean, this was clearly, from back in the day, this was a hand-designed CPU. I think CPUs nowadays are designed by like computer programs, like by AI. But this CPU was simple enough, or CPUs back then were simple enough that they could be designed by a human being. And this is the kind of optimization a human being would do. Like, how can I reuse all the circuitry that I've designed in here and reuse it to do something that I can already do? So I think I'm going to do subtract with carry the same way that they're doing it, because the other way of doing it is I just re-implement subtract with carry and I go through all of those processes we went with add with carry, except all of the weirdness is flipped. Like, I'd have to just rewrite the whole thing. So given that, let's just see if we can actually make that work. And let's actually try and test this. I'm actually going to put it in the same file with the add with carry tests. These are going to do some subtraction tests as well. Let's test the very first one we did that was super simple, which was, let's just see, we had a test for can add 0 with 0. And let's see, can subtract 0 from 0 and get 0. Weirdly, this is the one that's the same in both. So yeah, let's do the absolute one. And this should be all the same, except we want the carry flag. It adds the not of the carry, doesn't it? So we actually want the carry flag to be true in this case, I believe. Yeah. So that's the difference there, is the carry flag has to start at true on subtract with carry instead of starting at false. And again, you can see that it's been put on the programmer to get that set correctly. But it's really been put on the programmer to get the carry set correctly before you do any add or subtract. We expect the carry to be true because it should get set to, carry flag should be clear if overflow in bit 7, and this isn't going to overflow, so it will actually be set, yeah, and 0 will be true in this case. SBC Absolute. So we need a version of this test. Let's just see. It's going to be pretty much the same, except we pass in a different operand. Is that really it? Yeah, it's really exactly the same except that. So let's just do this. Seems a bit cheesy, this, doesn't it? But I mean, if this is going to be the only difference, if we're saying add, we'll do add with carry absolute, otherwise we'll do subtract with carry absolute, and everything else stays the same. Same number of cycles, and it's not ADC absolute anymore, it's yeah, I suppose we could do it like this. It doesn't read very well though, does it? And then we could put in a, it's always adding unless you say to subtract. That doesn't read very well. In fact, let's do this. Call it that. So it defaults to add, but here we're going to do subtract. think that's okay. That's not as pretty down there though, but let's try it like that. So we've reused all the test code that we've got, which is great because that means we don't have to rewrite very much at all. I just need to define this. Let's do it down here. So we want subtract with carry absolute, which is ED. So let's see what we got out of that. So we should have one test that does 0. I mean, I suppose 0 minus 0 and 0 plus 0 actually are the same answer, but when you're doing with carry, they're not. Should have a failing test, which we do. Can subtract 0 from 0 and get 0. So really you've got so many tests now that it just scrolls off the screen. I don't know how you get around that. Oh yeah, so the first problem is that didn't handle the instruction. So let's fix that. Let's copy our add with carry. ADC, which one am I doing? Absolute? Yeah. So this is SBC Absolute. Oh, subtract with carry absolute. So we can't just do, can we just do the normal? We can't do the normal ADC. This might actually pass. Oops. I wonder if it does. No, it doesn't. So that's good. Let's just see. I'm interested to see what we get if we just run it through ADC as it is and we don't actually try and fix it. So we've got subtract with carry implemented, but we've just called the ADC code instead. What doesn't it like about that? Let's have a look. Cycles is okay. The answer is wrong, which is kind of what we expect. The carry is wrong. 0 is wrong. Everything went wrong. Mostly wrong. The overflow flag didn't go wrong. Cool. Okay, so let's give this a try. Let's go find. In fact, what we should do then here is, in theory, all we have to do is negate the operand. Let's just see what happens when we go into there. That didn't work, but let's just see. We've got an operand of 0. Oh yeah, we don't. No, that's. Oh, that's done it. That's me forgetting how to do C++ or C, and it's bitwise negation. So I believe ADC with just a bitwise negation, is that going to work? If that works, I'll just make a subtract with carry that basically does that. Oh yeah, so that has passed. So that's actually pretty cool. If we can get away with that for everything, then we are cooking on gas. Now the next thing is, can you call a lambda from a lambda? I think the answer is no. I think these lambdas might have screwed me here. Do subtract, which just would call ADC with the bitwise invert of the operand. No, you can't call that. And a closing local variable cannot be referenced in the lambda body unless it is in the capture list. Oh, I can capture it. Really? Does that mean I don't have to capture any of that? I've never done this before, so here we go, we're learning. I want to capture it by, whoa, that's actually worked. Has it? Can capture it by reference or do I capture it by, don't know. Okay, so I'm capturing the function up there which captures all that, and all it really does is calls ADC and it bitwise negates it. Oh my god, is it this easy? Is it this easy? Well, it's worked. So that could be basically the entire of ADC implemented, because we just implemented the same one, at least for decimal mode anyway. Let's get some of our other tests and do, in fact, let's just write some. Subtract with carry absolute can subtract 1 from 0 and get 0. So the operand would be 1 from 0 and get -1. Let's just do some of these tests and see if this is going to pass. So operand is 1, answer is -1. What do we expect? It is negative. Did it carry? I don't know. Did it overflow? It did not overflow. Is it 0? No, it's not. So the only question then is, should it produce a carry? Should it produce a carry? The answer is the carry is clear if there's been an overflow. There's been no overflow with that because it's a perfectly valid calculation. So that should be true. Just going to convert the -1. Got a macro to convert it to a byte. It's storing it as signed. So that didn't work. Did I get that right? 0. Yeah, 0 minus 1 is -1. What's not right about this? Carry flag is 0, expecting true. Clear if overflow. So there was no overflow on that. So that doesn't work. Yeah, so I think this one's actually caught me out here, but not in the respect that the code is wrong. I think the code's working. I think it doesn't carry, which is actually what the value came out with. And I can do that if I actually do, if I do the actual, what was it? The actual subtraction here. So it's oh, let's get the right color. It's A. Whoa, let's do that right. A minus M minus, oh, terrible. 1 minus the carry. So we put a true in our carry, so that basically just ends up evolving down into A minus memory, and we were just doing 0 minus 1. And the definition of this is, if you actually do it as a subtraction instead of doing it as an addition, 0 minus 1 is the one you can't really do, and you can define that answer as actually being 1 1, which kind of gives you your borrow, if you know what I mean. It will give you that, and if you do 0 minus 1, you get 1 1 1 1 1 1 1 1, and there's the carry there. And we expect the opposite of that to be in the carry thing. So we actually expect a 0 in there because it did overflow, but we expect the opposite of that. So actually we expect it to be 0 on this one, and you can see that all the 1 set is our -1. So actually we do expect the carry flag to be false in this particular test, and that means that that does pass if you do that. So I've checked it by hand there, with the definition that 0 minus 1 basically gives you the kind of like 1 with a borrow, or you can think of it as 1 with a carry, but basically that's the definition of it. You can think about it as also as a 2-bit number that's negated. That's one way of doing it. So these are going to be tricky to verify basically, but I should do some more complicated tests, I suppose. I can subtract 1 from 0 with carry and get -2. That would be the other one. So in this case, if it did overflow, so that would be it has overflowed. 0 minus 1 minus another 1 should give us minus 2. Question is, do we expect a carry there? And the answer is I'm not sure. It is negative. It did not overflow. And it is not 0. Let's have a look what we get. This might pass, but I haven't really set the carry flag. It does. So the carry flag did turn out to be false in that one. At least we're getting the right answer there though. You can see we actually got, yeah, we got minus 2 as the answer. That is definitely working there. The question is it correct to have, so that would be clear if we had an overflow. So in this case, if we did the subtraction, it is 0, minus 1, and we are also subtracting the not of the carry bit, which is 1. Is that right? Yeah, so minus 1, and we're going to subtract another 1 as well. 0 minus 1 gives us our 1, 1, and then 1 minus 1 gives us 0. Puts a 1 in there, and then that gives us 0 minus 1 is 1, 1, and that's 1, 1, 1, 1, 1, 1, 1, and we get our carry in there, carry of 1, and we stick a 0 in there. So again, this test I think is correct. Yeah, and that should be minus 2. So yeah, if we put 2, and we can test that by, you put 2 in, if we did our 2's complement method, we put 2, oh my god, 0, 1, 2, 3, 4, 5, 6, as a 2. If we flip all that, and we add 1 to it, we get there it is, that's the answer, so there is our minus 2. So again, I think this is proving to be correct. So that's passed 3 tests now. So I think it's looking pretty hopeful that actually, not only is this the way that the actual CPU did it, but actually this is a really good way to actually do it in code, because, I mean, what did I actually write to do that? I just had to put the bitwise negation on there. And I didn't know you could do this with lambdas, which you can. So that's pretty cool. Let's do some more tests and let's verify that we've actually got this correct. I've got 3 now. What about if we did something that produced an overflow? So if we did, can subtract 2 negative numbers and get signed overflow. Okay. One of the ways to do that would be to do biggest number we can represent, smallest signed number we can represent. Let's set the carry to true, so we don't care about the carry in this one. Subtract 1. What would the answer to that be though? The real answer would be minus 129. Yeah, so if I did 128 and I subtracted 1, I'm doing this in byte mode. Yeah, it actually wraps around to 127. So I actually expect 127 in the answer. That has been a negative plus a positive should give us a more, a negative subtract a negative should give us a more negative number, and it gave us positive. So there has been an overflow. It is not 0, it is not negative, and then again the question becomes, did it carry or not? Looks like that one doesn't carry. The subtraction itself doesn't produce an overflow, but we set the opposite of that, so actually we do want something in the carry flag. Clear if overflow in bit 7, there was no overflow from that. That's what I just got when I did it on paper. Let's see if we got that one right. Yes. So I'm going to say that's correct. So this is all looking very good here. Can we do same thing with positive? Can subtract positive and negative number and get a signed overflow. Because if you take the biggest positive you can get, if you subtract a positive, subtract a negative, you should get a more positive number. So the biggest signed positive that we can have is 127. If we subtract -1 from that, we'd actually get the answer 128, because it'd be the equivalent of adding 1. So again, don't really care too much about the carry on this one. The answer is not negative. It did overflow. It's not 0. And again, question becomes, what should the carry flag be on that one? So it didn't overflow, and I think that's another one done. I bet you I've got the carry flag wrong here, have I? Oh, negative flag's wrong as well. Oh, negative is... Oh, because it is technically... Yeah, it is negative because it's actually wrapped around to 127 plus 1 is 128, but that's actually wrapped round to -128. Yeah, positive subtract negative should give me a more positive number, and it technically does, but not if you're doing signed. It's gone wrong, not if you thought that was a signed value. So all I got wrong is the carry flag. So this is not producing, it did not produce a carry. Clear if overflow in bit 7. It didn't overflow. Yeah, it does overflow if you're doing a subtraction, and then we set it to clear, we set it to false if it does overflow. So that's if you're doing a subtraction. I just did it on paper there. So again, is this correct? This is correct now because it was the wrong before. Yeah, I just checked it then because it is this. This is 2, 3, 4, 5, 6, 7. So if we actually did this as a subtraction, remember we're not caring about the carry flag here. It's 1 minus 1 is nothing. You get nothing, 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 and then you get 0 minus 1, and that gives you 1, 1. So you overflowed here. Overflowed. And that means we clear if the overflow, clear if overflow, and it was overflowing. So is there any other tests that are worth doing? Because I think this is pretty solid now. Did we do 0 subtract 0 subtract the carry? Did we do that one? I mean, it's going to end up being the same thing, but let's try that one. 0 from 0 and carry and get -1. So remember, the carry flag has to be false to say there was a carry from a previous subtraction. We do 0, 0, and we expect the answer to be -1. So again, the question is, does it carry? But is it negative? Yes, it is. Did it overflow? So that can't be an overflow, and it can't be 0. So the only question is, does it carry? And this is basically the same as -1 is all the bit set. So this will carry. So it should be clear. It's going to end up being 0 minus 1 because of the carry. And like I said, -1. Yeah, and it's going to carry all the way down. And then it's going to end up with an overflow. Let's see if I got that right. I'm doing that in my head. Yeah. So that one works. Is there anything else worth doing? Let's have another look at add with carry test that we did. See if we've got anything else that's good. We just had a random can add 2 unsigned numbers. I mean, maybe we can just put one in for that as well. 20 minus 17 gives us 3. Really, that's what it does. It doesn't, I don't think that one's going to produce a carry. Could be wrong on that. I keep saying it and then getting it wrong. It's not negative, there's no overflow, and it's not 0. Is that correct? I keep getting it wrong every single time. It's just the carry flag, isn't it? Oh, whoa, what is it? The answer's wrong. Oh. Because I added it. Whoops. Should be subtracting it. I got the carry flag wrong this time, didn't I? Yeah. Let me check that one again. If I do 20 minus 17. That's doesn't produce a carry. So clear if there's an overflow. It's set to true because it wasn't an overflow. Right, I got it wrong. Okay. That makes more sense. Clear if overflow, and there was no overflow, so we don't clear it. I'm pretty happy that that is subtract with carry actually working. I mean, I don't think I really explained it as well as I could. Oh, actually, here's one thing. I'm not actually calling subtract with carry. I'm calling ADC with the... I've actually got subtract with carry for the operand there. Let's just check that that still works. Yeah. So I don't believe I explained that incredibly well, but it really amounts to that subtract with carry, you can just do add with carry, and you can do on the bitwise negation of it because of the way the 6502 works, basically, because of this not carry bit. So that's actually making this work in the add with carry. So that must be how they're doing it. I mean, maybe that's how modern processors do it. I don't know. I didn't think it was going to be that easy. It was harder to write the tests, I suppose, than it was to actually do that. And I think I've got enough tests there. I don't know if there's anything else I should be testing. I mean, maybe once we get this running, we can do some more thorough testing. I'm going to have to do the rest for the other addressing modes anyway. Shall I do one more for subtract 2? Have I subtracted 2 sign numbers, negative numbers? I actually haven't. Let's do one more test quickly. And then we'll call it a night. Can subtract 2 negative numbers. Let's do that. So 20 minus 20. Again, we don't care about the carry really. Minus 20 minus 17 should give us minus 3. Now I don't know. Is it negative? Yes, it is. Does it overflow? No, it doesn't. Is it 0? No, it's not. Again, I just don't know what to put in the carry flag on this one. So it's not true, it's false, and that would imply that there was an overflow from that. Yeah, let's just do it in here. So negative 20, whoops. Negative 20 is 0, 0, 1, 1, 0, 1, 1, and negative 17 is 1, 1, 1. Which brings us out there. What do you think? See if that's there? We're expecting minus 3. We're doing subtraction. Let's see if I can get this to work. So let's try this. Nothing minus 1 is 1, 1. And then we've got nothing minus 1 is 1, 1. And minus 1 again. Actually, it's 1, 0, I believe. And then almost nothing minus 1 is 1, 1. That's 1, 1. That's 1 as well. That's 1, 1. That's 1, 1. That's 1, 1. I think. Yeah. So actually gives us, that is minus 3. That is the right answer there. And there is an overflow. Yep. So we got an overflow here. So that was overflowing. And remember, what do we do? We clear if there's an overflow. And there was an overflow. It's really cool how all this like binary math works out anyway. There you go. I'm happy with that. Right. I think I'm going to call it there. So that is the best I can do with my explanation of subtract with carry, is that basically you can, in the 6502, just bitwise negate the operand and do add, because the way they've done the not carry bit, it totally just works. Next time I'm going to move on and do the rest of the addressing modes for this, and then we've got full addition, subtraction. It's nearly a processor now. So I'll catch you for that one.